Okay, everyone. Assalamu alaikum. Let's begin then. So we were doing function transformations, and today we want to do some practice questions on transformations. So let's begin with this. Let me quickly remind you about the three transformations that we did. So about the six transformations, in fact, because we have three vertical, three horizontal. So there are two types of transformations: vertical or horizontal. If you have a vertical transformation, what happens is the graph moves vertically, the y coordinates change. And when do you have vertical transformations? When you have some functions, some operations applying outside the whole function. So if you have a function f of x, if something gets multiplied, if you have negative multiplied outside, that's a reflection in x-axis. If you have some number multiplied outside, that's a stretch along y-axis, scale factor that number that's multiplied. And plus minus b means there's a vertical translation. Plus means you're going up, minus means you're going down. In order to describe translation, you always write down a vector like this. And then we had three horizontal transformations. In horizontal transformations, the graph moves horizontally, only the x coordinates change, and the operations that are applied on the function are applied inside the function. So x is replaced with something else. So x can be multiplied with a negative sign. In that case, there's a reflection with y-axis as the line of reflection. If you have something, some number multiplied, that means it's a horizontal stretch along x-axis with scale factor reciprocal of that number. Okay, so if you have, for instance, f of 3x, that means the scale factor is 1 over 3. It's a horizontal stretch with scale factor 1 over 3. And then we had translation. If you add or subtract something inside the function, you add or subtract something to x. If you do plus something, the graph goes left. If you do minus something, the graph goes right. All right. That's what we did in the last session. Again, for this as well, you use the translation vector. In the vector, if you have minus, that means you're going left. However, in the function, if it's plus, that means left. Okay. So when you write it in the vector form, -4 means 4 left. However, in the function notation, if you have x plus 4 inside, +4 in the function notation would mean that you're going left. Okay, and -4 would mean that you're going right. In translation vector, it's different. So these are transformations that you need to know about. When you add or subtract something, you have translation. When you multiply or divide by a number, you have a stretch. When you multiply by the negative sign, you have reflection. When you do any of these operations outside the function, it's vertical. When you do any of these operations inside the function, that's horizontal. And then we talked about order of transformations. You can have a combination of these transformations as well. For instance, you can have all of these transformations applied at the same time like this, right? Vertical and horizontal. How do you decide which one to do first? Now, between horizontal and vertical, the order does not matter. So you can start from either vertical or horizontal, and that would not matter. So you can start from vertical or horizontal, right? Now, within vertical and within horizontal, the order matters. Okay, within vertical and within horizontal, the order does matter. In vertical transformations, you follow BODMAS. In horizontal, you do the opposite of BODMAS. So if you had to describe this, how would you do it? If you start with vertical transformations, you could say something like this. Number one, you could say it's a stretch. So I'm starting with vertical, okay? So vertical are these transformations, -6, multiplication of -6, and then +2, right? These are two vertical transformations. If we choose to start with vertical, we can say number one, we have a stretch along y-axis with scale factor -6. Now you could write it as two separate transformations. You could say it's a reflection and a stretch, and that's okay. Or you could write it as a single transformation as well. You could say it's a stretch along y-axis, scale factor -6, and that incorporates both reflection and stretch inside it, because when you have a scale factor of negative, remember what happens? The graph goes on the other side of the axis. So it will go on the other side of the x-axis. So it will take care of reflection as well. Okay, so we can combine these two transformations like this. We can say the scale factor is -6. Now in vertical, we are following BODMAS. So we're doing multiplication first. Okay, so that means stretch and reflection, they would be done first in this format. And then you do translation. So you can say the translation here is 0, 2. These are two vertical transformations. Okay, and then we think of the horizontal transformations. We have three horizontal transformations: reflection, stretch, and translation. Again, we can combine reflection and stretch if we want. And then we have this translation. Which one do we do first? Do we multiply with -4 first, or do we add subtract 1 first? It's horizontal now. In horizontal, we do the opposite of BODMAS. That means in this format, translation would be done first and stretch would be done second. So we can say the next transformation would be a translation. So we would have to do translation first. What translation? -1 means you're going 1 unit to the right. So the vector would be 1, 0. And then finally, you have stretch, and you can say it's a stretch along x-axis with scale factor -4. Okay, that's how you can describe the all of these transformations together. All right, these are the 4 transformations that are happening. Now, in case you have a situation in which 2 translations are coming one after the other. Only in that case, when you have 2 translations coming one after the other with no other transformation between them. So in this case, number 2 and number 3, they are one after the other with no other transformation between them. It is allowed to combine them as a single translation as well, and write this as a single vector as 1, 2. Okay, but if there was some other transformation between these translations, for example, if there was a stretch between them, then we would not be able to combine them. We can only combine when they are one after the other. Okay, so this is what it would look like, all of these transformations, if we were to describe them. So what you need to remember now is between horizontal and vertical, the order does not matter. But within vertical, you follow BODMAS. If you have something like this, you multiply first and then add. So that means you do stretch first and then do translation. If it's this format, again following BODMAS, you do translation first and then you do stretch or reflection. Okay. And then in horizontal transformations, you do the opposite. Opposite to BODMAS, if you have -5x + 3, BODMAS says that you should multiply with -5 first and then do addition. We would do the opposite. We would say do translation first and then do stretch. But if it's this format, BODMAS says that you have to evaluate the bracket first. So you do +4 first and then multiply by -2, but we have to do the opposite in horizontal transformations. So instead of doing translation first, we first do stretch and then we do translation. And that will be the order that we follow in this case. So in vertical, you follow BODMAS. In horizontal, you do the opposite of BODMAS. Okay, that's what we did in the last session. Now let's have a look at some questions. I hope you have attempted questions from the worksheet. And you can now let me know the problems that you have. I will start from the questions that are posted on OneNote first of all. We'll do a few of them first, and then we will look at questions from the worksheet. You can let me know the questions in the chat in the meantime, the questions that you have. And I'll start with some of these questions. Meanwhile, let's start with this one. Take a minute, have a look at this, and think of what we can do now. In each of parts A, B, and C, the graph shown with solid lines has equation y equals f of x. The graph shown with broken lines is the transformation of y equals f of x. State in terms of f the equation of the graph shown with broken lines. So we have this graph y equals f of x, and this broken lines graph is a transformation of that. What transformation is this? How do you get from this figure on the right to the figure on the left? It's a reflection. It's a reflection in y-axis. Do we call this horizontal reflection or vertical reflection? The movement of the graph is horizontal. The points on the right side, they're going to the left. The points on the left side, they would go to the right, right? So movement is horizontal. So we can say it's a horizontal reflection. Horizontal means something will have to change inside the function. X will change, okay? We have to write down the equation of this graph with broken lines. If we had to describe this, we would describe it as a reflection in y-axis. Okay, it's a reflection with line of reflection y-axis, and that's a horizontal reflection, but that's not what they're asking for. They're not asking us to describe this transformation. They want us to write down the function. What is the function going to be? It would be y equals f of minus x. Okay, so we multiply x with minus. That represents horizontal reflection. Okay, let's look at the second diagram. It says state in terms of f the equation of the graph shown with broken lines. Again, this is the original graph, and the broken lines one is the transformed graph. The size of the figure is changing, right? That only changes in case of a stretch, right? Translation and reflection, they do not change the size of the figure. So it has to be a stretch. Now, what stretch exactly is the shape? Is the length changing horizontally? Horizontally, it's 2 units wide. After transformation, it remains 2 units. So there's no stretch horizontally. Okay, what about vertically? The height of this figure was 2 units earlier. After transformation, it becomes 4 units. So it's becoming twice. So this is basically a vertical stretch. I'm just writing down for your understanding. It's a vertical stretch with scale factor 2. Okay. How do you represent that in the form of a function? It's a vertical stretch. So something has to happen outside the function. F of x, it's a stretch scale factor 2. We multiply by 2 outside. That's the equation of the function of this broken line, of the graph of the broken lines. Okay, let's move on. What about this now? This is the original graph that's going to this broken lines graph. How do we get from that first form to this form? Let's think about it. What transformation is this? This is translation, right? The graph is shifted to this other graph. Every point has moved there. How many units has it moved? 1, 2, 3, 4. 4 units left. So we're going 4 left. And 1, 2, 3. 3 down. 4 left and 3 down. If we had to write down a vector, that would look like this: -4, -3. That's the translation vector that we have. So it's a translation with this vector. Okay, but they've not asked us to describe this. They want us to write down the equation of the graph. What's the equation of the graph in broken lines? let's think about it. Is it horizontal or vertical? This is both, right? There's some movement horizontally, there's some movement vertically as well. So the movement is in both directions. We're going 4 units left, 3 units down. Okay, now how do we think about this? 4 left, 3 down. So we have to add or subtract something. Let's say this is f of x. Now, what do we do with this? Outside the function, we have -3. That tells us that the graph is going 3 units down. What about inside the function? We are going 4 units left. In horizontal transformations, it's the other way around, right? If you're going left, that means inside the function, we would have x plus 4. Okay, because plus 4 would mean that we're going left. The function is going to be f of x plus 4 minus 3. That's the function that we have in this case. Is that all right? Let's take a look at another example. This was another one that I posted on OneNote for you to attempt. Let's try this now. In the diagram, the graph of y equals f of x is shown with solid lines. The graph shown with broken lines is a transformation of y equals f of x. So we're going from the solid lines graph to this broken lines graph. Describe fully the 2 single transformations of f of x that have been combined to give the resulting transformation. So how do we go from this graph to that graph? That's the question. Which 2 transformations have been combined to give the resulting transformation? Now, how do we think about this? Which 2 transformations are these? One is very obvious. The size of the figure has changed, right? The size only changes when there is stretch. It does not change in reflection or translation, right? So there has to be some stretch at least. Now, what stretch exactly? Can we figure that out? Horizontally, the width was 2 units earlier. After transformation as well, it is 2 units. What about vertically? Vertically, the height was 1 unit earlier. Now it is 3 units, so it has to be a stretch by a factor of 3. So what do we write there? We say it's a stretch. Number 1, we have a stretch. Vertical stretch. You can either write vertical stretch or you can say it's a stretch along y-axis with scale factor 3. That's one transformation that is happening. The height is becoming 3 times as compared to what we started from. Okay, now, what else? What else is happening? What other transformation is happening? Any idea? What's the other transformation? Can anyone tell me what the other transformation is? So we figured out one of them. That's a stretch, vertical stretch, scale factor 3. The other is a translation, but what's the vector for that? What's the vector of that translation? 4, 2. Okay, so you're saying the translation vector should be 4, 2. Okay, so here's one of you saying 4, 2, then the other saying 4, 0. Which one of this is these is this? 4, 2 or 4 right, 4 up? Okay, so you're saying 4, 4. Okay, so we have all of these different possibilities now. Okay, so all of you agree that it has to be 4 units to the right. That's one thing that is happening for sure. Okay, so the graph is going 4 units right. So we can take any corresponding point. For example, if we take this point, 1, 2, 3, 4, this is going 4 units right. So 4 units right, that makes sense. But then you're saying it's going 2 units up or 4 units up. Okay. If you consider this bottom point, then that makes you think you're going 2 units up. 1, 2. But then those of you are saying 4, you are thinking of the top point, for example, this one, and you're saying, okay, you're going 1, 2, 3, 4, 4 units right, and then 4 units up, 1, 2, 3, 4. So is it 4, 2? Or is it 4, 4? Because one point is going 2 units up and the other point is going 4 units up. Or is it 4, 0? How does that make sense? If it's 4, 2, so if you're insisting on it being 4, 2, why is this point, this green point, also not moving up by 2 units? Why is this green point going up by 4 units? If it's 4, 2, then every point has to go up by 4 units, right? Why is this point going by 2 units? Why is this moving by 4 units? Whenever you have multiple transformations like this, keep in mind one thing. Once you have figured out one transformation already, so in this case, for instance, you have figured out that there is a vertical stretch, and that vertical stretch is by a scale factor 3. What you should do is, you should represent what the figure is going to look like after you have done this first transformation. What I mean by that is, once you apply this vertical stretch by a factor of 3, where is this figure going to go? Let's think about it. This bottom point, it's 1 unit up, that's going to go here. This point at 2, that is going to go to 6. And this point at 2, that's also going to go to 6. So once we have done that stretch by a factor of 3, you are already at this point now. The shape already becomes this now, after that stretch is applied. Okay? So stretch by a scale factor of 3 is already making this figure move up like this. And now, how do we go from this green diagram to this black diagram? How do we go from that green one to the black one? We just have to go 4 units right. We don't have to go up or down by any units. We just have to go right by 4 units. So the translation vector in this case, that's the second transformation that we have here, that is just going to be a translation vector 4, 0, because we're just going 4 units right. We're not moving up or down anymore because stretch has already taken care of the vertical movement. Okay? Does the order matter here? It does not, because one is vertical and the other is horizontal. We could do any of them first, although it's easier to figure stretch out first, right? Because if you try to do translation first, it's very likely that you would get that wrong. So you can figure out the stretch first. Once you have figured that out, you can see what the translation should be. Okay, let me repeat this. So stretch was easy to figure out, right? We figured out that it's a stretch along y-axis with scale factor 3. How did we figure that out? Because the size of the figure was changing. It was 1 unit high earlier, now it's 3 units high. So it's a stretch with scale factor 3. Now, once we apply that stretch on this original diagram, this is going to go to this green diagram already after we apply that stretch. How does that happen? This point at 1, that goes to 3. 1 multiplied by 3, that goes to 3. The point at 2, that goes to 6. And this point at 2, that also goes to 6. So after we have done the stretch, we already have this green diagram here. And now, how do we go from this green diagram to this black one on the right? That's the final one. We just have to go 4 units right. Okay, there's no vertical movement that's required anymore. The stretch already takes care of moving it vertically upwards. Okay, now the second part says, state in terms of y, f, and x the equation of the graph shown with broken lines. Okay, how do we do this now? F of x was the original graph. On f of x, we have applied these two transformations. Vertical stretch, scale factor 3, and horizontal translation 4 units to the right. What is the function going to be? Vertical stretch by scale factor 3 means we multiply by 3 outside. That's one thing that has to happen, right? We multiply by 3 outside. Translation 4, 0. We're going 4 units to the right. What does that mean? Inside the function, we do -4 because in the function notation, when inside the brackets, you have x minus something, that means you're going that many units to the right. Okay, that's what the function would be, 3 times f of x minus 4. All right, let's move on to the next one. That was from March 21. Let's have a look at another. Now, this is a tricky one. Find the translation that transforms the graph y equals this to this graph, y equals 5 over x minus 2 whole squared minus 3x plus 10. They've already given you a hint for this, that it has to be a translation. Okay, it has to be some translation. Okay. Now, what translation is this? Think about it quickly. Let me know what it should be. What's the translation vector going to be in this case? Two and 10. So outside the function, we're adding 10. That's what it looks like, right? And then inside, instead of x, we have x minus 2. We are subtracting 2. When we do -2, that means we're going 2 units to the right. So it should be 2 and 10, right? Or should it? That's not actually correct. It's not 210. It looks obvious that it's 210, but it's really not, because think about it. You are saying it's a horizontal translation of 2 units to the right because x is changing to x minus 2. That's what you're thinking, right? X is changing to x minus 2, so it should be 2 units to the right. And then outside the function, you have 10 added, so it should be 10 here. But the problem is, if x is changing to x minus 2, then why is this x not changing to x minus 2, the other x? Why does that remain the same? This should have also changed to, this x should have also changed to x minus 2 on the right side. That is not changing on the right side. And that's a problem. That means they have simplified it. They have simplified it. After transformation might have been something like this, x minus 2, but they have simplified it to get something like this eventually. So again, we have to break it down. We have to break it down. How exactly? One thing is clear from this, from the functions that were given, that x is being replaced with x minus 2. That is kind of obvious, that x is supposed to be replaced with x minus 2. But now let's stop there. The transformation that you're sure about, let's understand what happens to the function once you have already applied that transformation. So we are starting from y equals 5 over x squared minus 3x. That is the original function. Okay. One transformation is clear, that it has to go to x minus 2. So what we do is we say, let's do a translation x minus 2. Okay, x goes to x minus 2. Now, when we apply that transformation, what happens to this function? It becomes y equals 5 over x minus 2 whole squared minus 3 into x minus 2. This x should also change to x minus 2, right? Now, they have given the final answer in simplified form. So what we can do is we can simplify this and see what we get from this. We have 5 over x minus 2 whole squared minus 3x plus 6. So after doing the horizontal translation by 2 units to the right, we already have this form, which is 5 over x minus 2 whole squared minus 3x plus 6. We already have this form. And now what we have to do is, we have to go from this form to that final form. What do we have to do for that? In order to go from this form to that final one that we want, instead of 6, we want 10. How do you go from 6 to 10? What do you have to add outside the whole function? you have to add 4 outside. So you would say with x minus 2 inside, you add 4 outside the whole thing now, and that would give you 5 over x minus 2 whole squared minus 3x plus 6 plus 4, and that simplifies to 5 over x minus 2 whole squared minus 3x plus 10. That's the final result that we get. So what translation are we doing then? The translation is 2 units to the right. That was easy to figure out. So we figured that we applied that first to see what happens to the function after applying that transformation first. We got this already. And then what else do we have to do to get to the final result? We have to add 4 outside the whole function now. So the vertical transformation, the vertical translation is just 4 units. The vector would be 2, 4 and not 2, 10. So it's 2, 4 like this. Does that make sense? The translation here should be 2, 4 instead of 2, 10. So if you can figure out one transformation and you're sure about that, first you should apply that and see what more you have to do after that to get to the final result. So we figured out the horizontal transformation first. We applied that first, and then we saw, okay, we have to go from 6 to 10 now. So we just have to add 4 more, not 10, because 6 is already there after that horizontal transformation. Okay. All right. Let's have a look at some questions from the worksheet. Now, these were some good ones. I just copied them here in OneNote earlier already. Now, let's have a look at some questions from the worksheet that I uploaded. If you have any specific questions, please let me know right now. And we would have a look at those as well. Then I'll choose some myself. Any specific questions from the function transformation worksheet? Any specific questions from the function transformations worksheet? Okay, 5, 11. Okay, 5 is one that involves trigonometry. Okay. And 11 is also trigonometry. Okay, so we'll do the trigonometry ones as well. Let's start with some others first. So 5 and 11, so I'll keep that in mind. We'll do those as well. Let's start with some non-trigonometry ones first. This is question number 2 from the worksheet. I want to do a couple on quadratic functions in particular first, because they are tested a lot. This is from May, June 2022, C13, question number 4. And that's question 2 from the worksheet. Let me paste that here. Okay, we have a curve that has this equation. It's translated by -1, 3. Find the equation of the translated curve giving an answer in this form. Okay, now how do we think about this? The original function is y equals x squared plus 2x minus 5. We have to do this translation -1, 3. What does that mean? -1 means you're going 1 unit left. 3 means you're going 3 units up. Okay? -1 means you're going 1 left. 3 means you're going 3 units up. Okay, now, how is this going to look like in the vector form, or in the function form, in fact? If the original function was f of x, -1 horizontally, what does that mean? That means f of x plus 1. Inside the function, we should add 1. 3 vertically, that means we need to have 3 added outside the whole function. These are the transformations that are happening with x we should be adding 3. And to the whole with x, we should be adding 1. And to the whole function, we should be adding 3. So what does this become then? We have to make it f of x plus 1 plus 3. So replace x with x plus 1. So it becomes x plus 1 whole squared plus 2 into x plus 1 minus 5. And then with the whole function, you add 3. Okay, so these are two things that we are doing. We are adding 1 in place of x, and we're adding 3 to the whole function. And now you simplify this. They want you to give your answer in this form, in simplified form. You can simplify this and see what that gives you. X squared plus 2x plus 1 plus 2x plus 2 minus 2. And that simplifies to x squared plus 4x plus 1. That's the equation of the transformed function. Okay. All right. Now, what about the next one now? Part B. The curve with this equation is transformed to a curve with this equation. Describe fully the single transformation that has been applied. Single transformation that has been applied. So they've given you a hint here that there has to be one single transformation. One single transformation. All right. Now, what single transformation takes you from x squared plus 2x minus 5 to 4x squared plus 4x minus 5? How do we think about this now? Okay, now there are two ways of thinking about this. One is quicker, but it's harder to figure out. I'll tell you that way first, which is quicker, but a bit harder to figure out. 4x squared plus 4x minus 5. In this case, it won't be that hard because they've told you that it's a single transformation, so it'll be relatively easier. And that's just thinking of it in your head and thinking of how you can go from this form to the form, eliminating some possibilities and figuring out what possible operations could you apply to the function to go from this form to this form. Now let's think about it. This is minus 5 in the original function. In the transformed function as well, this is minus 5. Minus 5 is not changing. It is what it was before. That's not changing at all. That means whatever transformation is being applied, that is not applying to the whole function. Okay? So if we were, for example, multiplying the whole function by minus, let's suppose, then this would have changed to plus 5. If we were multiplying the whole thing by some number, let's say 2, then 5 would have changed to 10. If we were adding something outside the whole function, then again, this constant would have changed to something else. So that's not happening. What that tells us is it's not a vertical transformation, right? Because if it was a vertical, something would be changing with the whole thing, and that's not happening. Okay, so it's not a vertical transformation. It is some horizontal transformation, and you can notice that here as well, that this is changing to 4x squared, this is changing to 4x. Now, what transformation can it possibly be in the horizontal direction? We're not multiplying by minus, that's also clear. We're not adding or subtracting something, that's also clear. We're just multiplying something. Now, what exactly are we multiplying? How do we figure that out? What are we replacing x with so that this function changes to that? If the original function was f of x, what are we changing inside the function? What are we multiplying x by to get this transformed function? Think about the second term. 2x is going to 4x. If we multiply this by 2, that gives us 4x, right? So it's possible that x is being multiplied by 2, so it becomes f of 2x, right? Because that would change 2x to 4x. And this x as well, if you replace this with 2x, this becomes 2x whole squared. And that gives you 4x squared. That's exactly what you have as the first term as well. So that is the transformation that is happening. F of x is going to f of 2x. How do you describe that transformation? You would say it's a horizontal stretch or a stretch along x-axis, with scale factor reciprocal of this number. Which is going to be 1/2. That's what they're asking for. This is what you would write. It's a stretch along x-axis with scale factor 1/2. All right. Now that's one way to figure out this transformation. You can do it this way. A more general way that will work for any question like this, for any quadratic function, is going to be like this, that whenever you have to figure out what transformation is happening to a quadratic function to take it from one form to another form, generally what you should always do is complete the square for that. Completing the square is going to make this much easier to spot that what transformation is happening. For example, in this case, you know that x squared plus x plus 5, x squared plus 2x minus 5, this is going to 4x squared plus 4x minus 5. One way is to think of it in your head, try to figure out, okay, what could change to this function to give us that other function. That's trickier. An easy way to do this is that works for any question like this. When you have to figure out what transformation is happening, you complete the square for both of these functions. Let's do this for the first one. It becomes x squared plus 2x. You add 1 squared, you subtract 1 squared, and you have minus 5 outside. These first three terms give you a perfect square, and that becomes x plus 1 whole squared minus 6. Okay, so that's the original function. What about this transformed function? What transformation is happening there? Again, you can try to complete the square. Take 4 common, first of all, for that. You have x squared plus x left. Inside the bracket, you can keep minus 5 outside. Coefficient of x is 1. Divide that by 2, square that, and add that and subtract that here. These three terms give you a perfect square, so it becomes y equals 4 into x plus 1/2 whole squared minus 1/4 minus 5. When you simplify this, that's going to give you 4 into x plus 1/2 whole squared. 4 into minus 1/4 is minus 1, minus 5 outside, that becomes minus 6. So this original function is going to this function. Now, what exactly is changing? You have 4 multiplying outside, and something is changing inside as well. Now, in this form, you see there are 2 things happening. There's some number multiplying outside, and also there's some change inside the function, so that would be 2 transformations. In the question, it says, you need to describe fully the single transformation. You can't write 2 transformations. You have to write only 1 transformation. Now, how do we do that? In this case, since you want only 1 transformation, one way to do that would be that you take 4 inside the bracket. How can you do that? You can write 4 as 2 squared. We've done this in quadratics before, right? If you want to take this number inside, you can write it as 2 squared so that the powers become the same. And now you can multiply 2 inside, and that will give you y equals 2x plus 1. 2 into x is 2x. 2 into 1/2 is 1. So 2x plus 1 whole squared minus 6. That's what we get. And now you can spot what is changing. X is being replaced with 2x. So f of x is going to 2x. That means it's a stretch along x-axis, scale factor 1/2. Much longer than the previous method. In this case, you could have spotted it directly like this as well. But if it's more than 1 transformation happening, it won't generally be possible, or it will be very difficult to figure it out directly like we did in this question. In those questions, generally, you would first have to complete the square to understand those transformations. And that's what we did here. This is another way to think about this as a more general way that would work for most questions like this. Is this all right? Any problems? So that's something that you need to remember now. Whenever you have to do transformations, whenever you are given some transformations of some quadratic functions and you have to spot what transformation is happening, what you should do is you should complete the square first and use that completed square form to understand what transformation is happening. I'll do one more question like this and then we'll move on to trigonometric functions. One quadratic function in which we have to figure out the transformation. Let me find one from here. This is one very good question as well. Question number 6. I'll do this as well. But before this, let me find one. Okay, so 7 looks like that form. Okay, let's do question number 7, and then we look at trigonometric functions next after that. Okay, question number 7 from this worksheet. Okay, it says functions f and g are both defined for all real values of x and are given by this and this. Describe fully the transformation that maps the graph of y equals f of x to the graph of y equals g of x. How do you go from this function to this function? Now, you see, just looking at these functions, it's not that easy to figure out, right? Minus 2x is changing to plus 4x, 5 is going to 13. It's hard to spot directly like this. What you would do in such problems would be, you would complete the square of both those forms. X squared minus 2x plus 5, that is going to x squared plus 4x plus 13. Now, what transformation is happening? Let's complete the square, and that will make it much easier to spot. X squared minus 2x plus 1 squared minus 1 squared plus 5. These three terms give you a perfect square. So that's x minus 1 whole squared minus 1 plus 5, that becomes plus 4. And then the other function is x squared plus 4x plus 2 squared minus 2 squared plus 13 outside. This is a perfect square, which is x plus 2 whole squared minus 4 plus 13, that becomes plus 9. So we have to go from x minus 1 whole squared plus 4 to x plus 2 whole squared plus 9. That's the transformation that is happening. Okay. Now, how do we write down this transformation? How do we describe this transformation? What is changing? Outside the function, 4 is going to 9. How do you take 4 to 9? We'll have to add 5 for that. How do you go from minus 1 to plus 2? For that, you would have to add 3. So this is a translation. Which translation? We can say something like this. If the original function was f of x, minus 1 is going to plus 2. What are we doing to this function? What are we doing to x here? We're adding 3 to that. Right? Minus 1 plus 3, that gives us 2. So it should be f of x plus 3. Outside the function, we have 5 adding So that becomes plus 5. So what translation is going to be, is it going to be then? They've asked us to describe the transformation. We would say it's a translation. What about the vector? 3 units left, that's -3. 5 units up, that's 5. This is what we write down there. Now, there are no marks for the working here. The 2 marks are for just writing this down. Okay, so some people might be able to do this in their head, although this one is much more difficult to spot mentally. But you don't have to write down the function form here. You can write down the vector directly. That's what is required in this question. Okay, I hope that makes sense. That was question number 7. Let's look at some in which you have trigonometry involved now. This was 7. Now you've asked about 5. Let's have a look at that. Question number 5. Okay, let's try this now. Okay, question 5 from the worksheet. Now, before we do the trigonometry ones, remember what we discussed about trigonometric transformations earlier. In sine and cos functions, the number that's multiplying outside, that represents the amplitude. And the number that's adding or subtracting outside, that represents the baseline of the graph. Remember that? And in horizontal transformation, the number that's multiplying inside, that changes the period of the graph, right? So if you're multiplying by 2x, for instance, the period gets halved by that, okay? If you're dividing by 3 inside, the period gets multiplied by 3, okay? So that's something that you need to remember for trigonometric functions. For sine and cos in particular, the number multiplying outside represents amplitude, and for all the functions, the number adding, subtracting outside represents the baseline, and the number multiplying with x inside, that changes the period of the graph. The period gets divided by that number. We did this in trigonometry. Now keep that in mind while we look at the trigonometry problems now. The graph of y equals f of x is transformed to this graph. Describe fully the 2 single transformations that have been combined to give the resulting transformation. Now, this one is fairly straightforward, the first part. 2 is multiplying outside, that's a stretch. So we can say it's a vertical stretch or a stretch along y-axis scale factor. 2, that's one transformation that's happening. Number 2, -1, that means it's a translation, and it's a translation 1 unit to the right, the vertical component is 0. That's a translation. That's the transformation that's happening in the first part. Part B, this curve is reflected in the y-axis and then stretched by a scale factor 1/3 in the x direction. Write down the equation of the transformed curve. Okay, now how do we think about this part B now? Let's write it in the function notation first. That makes it easier to understand. Reflected in the y-axis. The line of reflection is y-axis. Is that vertical reflection or horizontal reflection? Line of reflection is y-axis. That's horizontal reflection. The points on the left go to the right. The points on the right go to the left. That's horizontal reflection. Okay. So what is the graph going to change to? If the original graph was, let's say, f of x, after this reflection, it becomes f of -x. And then you are stretching this by a scale factor of 1/3. Scale factor 1/3. What do you multiply that by inside? If the scale factor is 1/3 in horizontal transformation, this is horizontal transformation, right, in the x direction. If the scale factor is 1/3, inside the function, you have reciprocal of that. So it would be f of -3x. This is what the resulting function is going to be. Reflection changes to f of -x, and then you multiply it by 3. It should be f of -3x. Okay, that's what you have to do now. The original function is y equals sine of 2x minus 5x. That has to go to f of minus 3x. So you just replace x with minus 3x, so it becomes sine of 2 times minus 3x minus 5 times minus 3x, and that gives you sine of minus 6x plus 15x. And that's the function that we were looking for. This is the transformed curve. Sine of minus 6x plus 15x. Is that all right? Make sense? That was question number 5 from the worksheet. Let's have a look at another. You're saying question 11. Let's try that. Okay. Question number 11. Let's have a look at this one now. Copy this here. This is June 20, paper 1-2. Okay, so this is question number 11 from the worksheet. Let's have a look at this now. It says functions f and g, they are defined such that f of x equals this and g of x equals this. State the ranges of f and g. Now, the first part, we can do that using what we discussed in functions, how to find range of trigonometric functions. Sine function, if it's completing one full cycle, it goes from -1 to 1. Is it completing one full cycle here? It is actually completing one full cycle because its original interval is from 0 to 2 pi. However, so the period for sine x is 0 to 2 pi. But since we are multiplying it by 2x, multiplication by 2 divides the period by 2. So the period is going to be pi. So sine of 2x, it does complete one full cycle from 0 to pi. So in order to find the range of this function, all we have to do is replace this thing with -1 once, and then you replace this with 1. And that will give you the extreme points of f of x. That's one way to do it. Input sine 2x as 1, and then you input sine 2x as -1, and see what the function gives you in both of those cases. 2 minus 3 into 1, that is -1. 2 minus 3 into -1, that gives us 5. So we can say the range of the f of x function, that is from -1 to 5. That's the range of the f of x function. That's one way to do it. If you find it hard to think of how the period is changing, the other way, the simpler way, is just to use the table function on a calculator. We did that the other day as well. Just use the table function on your calculator. Go to the table function. Now put that function there. Make sure your calculator is in radian mode. For this, 2 minus 3 sine of 2x. Put that there. Start at 0, end at pi. And then the interval should be small enough that you have like 8, 9 values. I generally recommend for range questions, you divide the interval by 8. Okay, pi divided by 2 once, that gives you pi over 2. Divided by 2 again, pi over 4. And divided by 2 again, that's pi over 8. Okay, so that will give you 9 values, and that's going to be enough. pi divided by 8. That's the step that we use here. Look at the table now. See whatever is the highest value. Let's look at the smallest value first. What's the smallest value? We've got -1. Do we have any other value smaller than that? No. Okay, so smallest value is -1. So you can directly write, okay, smallest is -1. Then you look for the biggest value. You have 2 above, right? Is there any other bigger value? Let's check that. 4.125. 5 is the bigger value. So you write 5 here. And you say the range is from -1 to 5. Okay, you can do this from calculator directly as well. And that will be fine. Now they're saying find the range of g of x. What about the range of g of x? G is -2 times f of x. -2 times f of x. Now, one way to do that is you have the range of the f of x function. You multiply these numbers by -2. So you have -1 as one extreme value and you have 5 as the other extreme value. You can say, let's multiply -1 by -2. What does that give you? 2. Let's multiply this by -2. That gives you -10. So g has to be between these two values. Now -10 is the smaller value, 2 is the bigger value. So the way we write this is, we say the range of g of x is from -10 to 2. That's the range of the g function. Again, that's one way to do it if you want to do it yourself. The other possibility is to use the calculator again, use the table function on your calculator. And instead of the previous function now, you have -2f of x. How would you do that? So we wrote this function there already before. Multiply this whole thing by -2. -2 times this whole thing. Right? That's -2 times f of x. Keep everything else the same. We have the same interval 0 to pi. And you have this table. Look at the table now. What's the smallest value in the table? Okay, we've got -4 here for now. Do we have any other smaller value? -10. And that's it. -10 is the smallest value. So we say, okay, that's the smallest value. And then the biggest value, we have 2 here. Anything that's bigger than that? No, 2 is the biggest value. So we say the range is from -10 to 2, and that's our final result. Okay, that's the first part. Now the second part says, the diagram below shows the graph of y equals f of x. Sketch on this diagram the graph of y equals g of x. Now that we know what the range of the function is, f of x is going to look, this is f of x, right? We can mark these points now. The maximum point of f, what's that? That's 5. So this point is supposed to be 5. The minimum point of f is -1. So that means this point is supposed to be -1. Baseline is going to be exactly in the middle. This is going to be the baseline. This is 2. Baseline is at 2. So that's the f of x function. What about the g of x function now? What about the g of x function? We have the lowest value for that, -10, and the highest value of that, that's 2. Let's mark those points. This is 5. This might be -5 here, and then double that to get -10 somewhere around here. -10 is the smallest value, 2 is the biggest value. Where's the baseline going to be? In the middle of these two values, -10 and 2, the middle is going to be at -4. That will be here. Here is going to be the baseline of that function g of x. And now you have to sketch that graph. How do you do that? We made the table for that already. We can make a table like this. When x is 0, we've got -4. So the graph starts at this point. And then we have 2 at pi over, so this is pi, right? In the middle here, we would have pi over 2. And we divide that by 2 again, that will be pi over 4. So at pi over 4, we've got 2. So this value is 2. And then next, after that, we have -4 at pi over 2. And then -10 at this number here. This would be 3 times pi over 4, right? So that would be 3 pi over 4. So the other next point is at -10. And then at pi, it is -4 again. And you have these points, you can draw that shape through these points now. Remember, the shape of the sine function, it's either going to be like this, or if it's reflected, it can be like this. It's one of these two shapes. You can see whatever shape you get from these points, it's going to look like this, and then this. And then it goes like this. That's the sketch of -2 of f of x, which they're calling g of x. And that's the other graph that you had to sketch there. Okay. Now they're saying describe fully a sequence of transformations that maps the curve f of x onto h of x. Okay, and what's h? H of x is g of x plus pi. All right. Now, what does that mean? We have to go from f of x to h of x. Okay, so first of all, f of x is going to g of x, which is -2f of x, right? And then it is going to h of x. H of x is g of x plus pi. Okay, so what are the transformations that are happening first? We are multiplying the whole thing by -2 outside. What transformation is that? That's a vertical stretch. That's a vertical stretch, scale factor -2. Right? Or we can say it's a reflection in x-axis and a vertical stretch with scale factor 2. Or we can combine this as well and just write it as a single transformation. We could say it's a stretch along y-axis with scale factor 2. Sorry, -2. And then we have this horizontal transformation, x plus pi. What's that going to be? Plus pi means you're going to the left. So it should be minus pi and 0. And that's the translation that we have. Plus pi means we're going pi in its left. So the translation vector is going to have minus pi like this. Minus pi 0. That's the translation vector. These are the transformations that are being applied to go from f of x to h of x. Make sense? Any problems with this? No problems? Okay, let's have a look at a couple of more questions and now slightly more tricky ones on trigonometry. So that will be quick though. It should not take that much time. This is question number 9 from the worksheet. We have this weird looking graph. Now for this, you need to remember the trigonometric transformations that we studied earlier. They will make it easier to understand. Question number 9. In the diagram, the lower curve has equation y equals cos theta. This curve has equation y equals cos theta. And the upper curve shows the result of applying a combination of transformations to y equals cos theta. Okay, find in terms of a cosine function the equation of the upper curve. Now, what we should do first is we should figure out what transformations are being applied here. What transformations are being applied? First of all, let's think about the vertical transformations. This lower graph is the original cross graph, right? The baseline is at 0 in the original graph, x-axis, right? That's the baseline of the original graph. What happens when this is transformed to this other graph? What's the baseline of that second graph? The highest point is 5, the lowest point is 1. Baseline is going to be exactly in the middle of those 2 points. That means it's going to be at 3. So the baseline is going up by 3 units. Okay, what does that mean? That means outside this whole function, so if the original function is y equals cos theta, outside this we have 3 adding. right? The whole graph has shifted above by 3 units. That's one thing that is happening. Then what about the amplitude? It was 1 earlier. Amplitude was 1 earlier. What happens after transformation from the baseline? The vertical distance is now 2. So the amplitude becomes 2. That means we have to multiply by 2 outside as well. So the whole thing gets multiplied by 2, right? The function gets multiplied by 2 outside because the number outside represents the amplitude. It's a vertical stretch, scale factor 2. So we have 2 multiplying outside. And then, so that takes care of the vertical transformations. What is happening horizontally? Let's think about that. Horizontal transformations. Horizontally, the period of the graph was 2 pi earlier. That's the original period of the graph. After it is transformed, the period now becomes 4 pi. So period is being multiplied by 2. Period is being multiplied by 2. Remember what used to happen in this case? If we had y equals cos of 2 theta, that actually would mean, or let me use another number, let's say 3 theta, that would mean the period is going to get divided by 3. So whatever the original period was for cos, the original period is 2 pi, it gets divided by 3. If it's multiplying by 2, in this case, 2 pi is going to 4 pi, that would mean inside the angle, we would have division like this, we would divide by 2. So if the period is getting multiplied by 2, the angle gets divided by 2 like this. So this is what the function is going to look like. 2 into cos of half theta plus 3. That's the function. Okay? Because period is getting multiplied by 2. So the number inside that gets divided by 2. We've done this in trigonometry. Another way to think about this is if you find it hard to do it this way, you can remember that formula that we did, that if we have y equals cos of b theta, then that means that the new period of the graph is going to be the original period divided by that number b that's multiplying. What's the new period? Period of the transformed graph, that's 4 pi. What's the original period of the cos graph? That's 2 pi divided by b, and b turns out to be 1 over 2. So this number here has to be 1 over 2. You could write this as half theta or theta over 2. It's the same thing. That's the function that you have. All right. I hope that makes sense. Now, one last question, and that's on tan. In sine and cos, figuring out the baseline is easier because you just find the difference between, you just find the midpoint of the maximum and minimum points. But when it's a tan function, finding the baseline is not as straightforward as finding the midpoint of the maximum point and the minimum point, because in this case, there's no maximum, there's no minimum, because the graph is going towards infinity or negative infinity. Okay, so how do you figure out what transformation is happening in a graph like this? When you have a tan graph, they're saying the diagram shows part of the graph of y equals this. Given that b is between 0 and pi, b is this translation, state the values of the constants a, b, and c. Again, we need to figure out what transformations are happening to the tan function and figure out what the values of a, b, and c are using that. This is the graph of the transformed function. Okay. What does a represent? In this case, a does not represent the amplitude, right? It used to represent the amplitude in sine and cos functions, not in tan function. But c still represents the baseline. That's the easiest to figure out, so we can start with that. Remember what the tan graph looks like. This is what the tan graph looks like. Its baseline is at x-axis. And notice, around the baseline, the shape of the graph changes. So if it was going like this earlier, after that, it goes like this. So at that baseline, the direction of the curve is going to change. So if you have to figure out the baseline of this graph, you have to figure out where is the direction of the graph changing. Let's look at it closely. It's going in one direction until this point, like this. And then at this point, it changes direction and becomes this. And that basically tells us that the point that was supposed to be at the origin earlier, because originally the tan graph looks like this, right? From the origin, that point has gone from the origin to here. The baseline that was at x-axis earlier, now it is going to be above here at 1. That means the value of c therefore is going to be 1. So c is supposed to be 1 using that logic. Okay. Now, vertically, we are going 1 unit up. The origin, the point at the origin is going 1 unit up. What about horizontally? Horizontally, it's going 5 or 4 units to the right. That point at the origin earlier, that's going 5 or 4 to the right. What does that mean? It's a horizontal translation, 5 or 4 units to the right. That's why we have this minus sign here. It's going right. That's why we have minus there. What's the value of b? The value of b should be pi over 4. Okay, because it's going pi over 4 units to the right. We do minus pi over 4 there. So the value of b is pi over 4. And then finally, what about a? That's the vertical stretch. What vertical stretch is happening here? How do you figure that out now? For this, you need to remember for the tan graph, remember when we used to draw this graph, from 0 to 45 degrees, or from 0 to pi over 4 radians, the graph goes 1 unit up. Right? From 0 to 45, the graph is going 1 unit up. For a 45-degree interval, from the starting point, it's going 1 unit up. Now, in this case, this is where the graph is supposed to start from, right? This is the point corresponding to the origin in that original graph. From this point in this pi over 4 interval, after this, how much is the graph going up? It's going up by 2 units. Earlier, it used to go up by 1 unit. Now it's going up by 2 units. That means the scale factor of the stretch, it has to be 2. So this number a has to be 2. So the value of a is 2, the value of b is pi over 4, and the value of c is 1. That's what we write down here. And these are our final results. B and C were easy to figure out. Another idea could be that you find B and C first, which are easier to figure out. And then you take one random point on the graph. For example, you could take this point here. Take this point, input this point as the values of x and y. You have A and C already known. And you can find the value of, you have B and C already known. You can input x, y, b, and c, and you can find the value of a from that. Slightly longer, but if you can't figure out the value of a, another way, if you find it hard to think of directly, then that's another way. If you know every other constant, you can input a point and find that remaining constant using that. Okay, I hope that makes sense. That's it for today. I'll see you again in the next class. Tomorrow, or in fact, whenever we have our next class, we're starting equation of circle now, inshallah. Okay, that's it for today. I'll see you again on Monday now when we start equation of circle. We might need to do an extra class next week as well, but that will be the last one. But I'll confirm that. And remember that the timings are also changing next week as posted on the group. We'll have our class from 4:15 to 5:35 from next week onward, inshallah. All right, I'll see you again on Monday then. Allah Hafiz. Bye.